Hi, everyone. Today we are going to finish our discussion on center of mass. So last time we left off with using calculus to find the center of mass of a uniform density rod, right? But if the density is uniform, then the center of mass is just kind of in the middle, so that's not really much of a challenge for us. So here we actually have a non-uniform density rod. Okay, so it says now, suppose that a thin rod has a non-uniform density that varies linearly with x according to the function lambda equals alpha x. Where is the center of mass for this rod? So it gives us information right here to tell us that this is a linear density, right? So linear density lambda is dm divided by dx, and then it tells us there that dm will be lambda dx. Now we're going to set up our integral just like we did last time. We have the x center of mass equals the integral of x dm over the integral of dm, right? But now when we substitute this in, lambda now is not just density, is actually a function of x. It varies as you move down the rod. So what we'll do is we will substitute this in, right? So we've got the integral of x lambda dx over the integral of lambda dx, right? But now lambda is a function, so now we will have the integral of alpha x squared dx divided by the integral of alpha x dx. Now, these are also all from 0 to L, right? We're integrating across the entire length of the rod, length being given as L right here. So we will do these integrals separately. We will do, let's say, the bottom first. We have the integral from 0 to L of alpha x dx. That would give us alpha x squared over 2. From 0 to L, which is just alpha L squared over 2. And then the top integral from 0 to L is alpha x squared dx. So this will just look slightly different. You've got x cubed over 3 from 0 to L, which then gives you alpha L cubed over 3. Now we'll plug this back in up here. You've got alpha L cubed over 3 divided by alpha L squared over 2. Okay. Now, notice here that the alphas are going to cancel, and we'll talk about that in a second. And then the L squared could also cancel 2 of these 3 L's. And now you will get L over 3 times 2 over 1, because we're dividing by 1/2. You can just multiply by the reciprocal. So you get 2/3 L. So if this rod has a linear non-density function, right? But it's linear, right? That means that the function alpha x, okay, there is no x squared or x cubed or even 1 over x. It is alpha times x. That could be 2x, 7x, 7,000x. We don't know how it varies, but it varies linearly. So with every unit of measure you go forward, you will multiply by alpha. Now it turns out that it doesn't matter what alpha is because it is a linear inclination. It's going to increase linearly. So it doesn't actually matter if it's increasing 7 times or 7,000 times because as you can see down here, the alpha got canceled anyway, right? So if it is linear with the function alpha x with no plus b or anything on the end, just alpha x, the center of mass will be 2/3 of the way down the length. So that's pretty cool. I like that problem. Next, we're going to find the center of mass of this weird shape. So we have this piece of sheet metal that is basically composed of 3 different density metals. We've got the blue metal with a density of 18 grams per square centimeter. The red metal has a density of 10 grams per square centimeter, and the gray has a density of 5 grams per square centimeter. Now, what you should notice here is that this is using area, right? That is not grams per cubic centimeter or grams per centimeter. we're all used to volume and having a cubic unit, and usually, well, I guess over the last couple problems, we've used linear, right? It was just something per meter. Now this is going to use area. So if you remember from our last video, sigma is area density, mass divided by area, or dm over dA, however you'd like to show that, right? We're not going to use the calculus method because here we just have a graph. We can actually look at this graph and find the areas, right? So what we're going to do is we need to find the center of mass for this. So our center of mass is going to be the same as it has been before, right? You've got x center of mass. We'll take the mass of the blue times the x center of mass of the blue plus the mass of the red times the x center of mass of the red plus the mass of the gray times the x center of mass of the gray divided by all of the masses summed up. Now, first, so we need m and x for each of these. You can see here that if we do sigma times a, you'll get mass. So we will find that. Now to find the x and y center of mass is going to be kind of tricky. What we'll do is we'll actually just use this graph because everything is pretty nice and neat, this diagram here. So for example, if we're looking at the blue, right, it is 20 centimeters wide in the x, so the middle would be 10, right? That's your center, since it's uniform density. Then it goes from 20 to 30, so your mid-range there would be 25, right? So you've got 10, 25. So we'll work through these real quick to get all of these numbers. We need the mass of blue, okay, so that is its density times its area. So we've got 18 times the area, which is, you can see there is 20 times a height of 10. So that would be 200, right? 18 times 200. That will give us a mass of 3,600 grams. I'm going to use kilograms to make these numbers a little bit more manageable. Then we need mass of red. Mass of red, you take the density of 10 times its area. They all seem to have 200 area, right? That goes 10 to 30, that's a difference of 20, then 0 to 10, difference of 10, so that's 200 also. So that will give you 2,000 grams, which is 2 kilograms. Then the mass of gray, again, 20 long, 10 wide, that's 200, so you've got 5 times 200, which gives you 1,000 grams, which is 1 kilogram. Okay, so we've got the masses. Now we need the middle points. If we look at the red, from 10 to 30, your midpoint would be 20. From 0 to 10, your midpoint would be 5. So let's write these all out. Okay, you've got x of blue, midpoint is 10 like we have here. The y of blue, midpoint would be 25. Okay, and these are all relative to this origin right here. Next, we have the x of red. The middle point would be 20 centimeters. And then the y center mass of red would be 5 centimeters. I don't have a gray, so I'll just use green. The x center of mass for gray is going to be 5, right? The midpoint between 0 to 10 is 5 centimeters. Then the y center for the gray would be 10, right? 0 to 20. It's going to hit 10 centimeters. Now all we need to do is take those numbers and plug them in, right? Because we've got those numbers. We've got 3.6 times 10 plus 2 times 20 plus 1 times 5, all divided by 3.6 plus 2 plus 1, so divided by 6.6 kilograms. And that will give you about 12.27 centimeters. And if we do the same thing for the y, I'll just go off this. So we have 3.6 mass of blue times the y of blue plus the mass of red times the y of red plus the mass of gray times the y of gray, all divided by 6.6. This will give you about 16.67 centimeters. So the center of mass is going to have an XY point of 12.27 by 16.67 centimeters. Okay. And if you notice here, I'm going to clean up this diagram here so we can look at it. If we go 12, right, that is a little bit past 10, and then we go up 16, that's a little over halfway here. So our center of mass is about right there, which means that this object couldn't balance on its own up on one point, right? Most objects, you can balance them if you find their center of mass. Let me find the mass of this pencil, right? Center of mass, you just balance it on a point, right? You can do that with two-dimensional, three-dimensional objects, three-dimensional object, right? But this one can't because it's a weird shape, and the weird non-uniform density means that its center of mass is actually off the object entirely. So this one can't actually balance without support, which is interesting. Now, what if there was a hole bitten out of it? Now we have this uniform sheet of metal. I'll just read it. A hole of uniform diameter of width A is cut out of a square sheet of metal of uniform density with side width 2A. Where is the center of mass? Okay, so we know the side of the square, that equals 2A. We know that the diameter, which really just goes from here to here, right? That would be A, diameter of the circle. Now the uniform density is going to help us a lot. Uniform density, we also know that we're just dealing with area, right? So uniform density will be sigma, that is mass divided by area. Now we want to know where is the center of mass. So this is something we've never done before, is we're actually going to subtract as we do our center of mass. Here, what we'll do to find the x center of mass, we'll take the x center of mass of the square, and we'll subtract the x center of mass of the circle. Okay, so we're going to do the math as if the circle is not there, right? We're going to find the center of mass of the square, and then we will subtract the center of mass of the circle and just take out that piece and then figure out where it's going to go from there, right? So this is actually going to look like this. We'll take the mass of the square, x of the square, minus mass of the circle, x of the circle, divided by mass of the square minus mass of the circle. Okay. But first, we need the mass of the square, mass of the circle, and the x components of all of that. So we see up here that mass is sigma times the area. So this is going to get tricky. Let's see, the sigma is going to be the same for all of them, so we're just going to leave sigma alone. And this is all mostly going to be done using symbols. So sigma is sigma. The area of the square, right, is the length of the side squared, which would be 2a squared, which gives you 4a squared. Then the area of the circle is what, pi r squared? Pi r squared, which would be pi times diameter over 2 squared. So that gives us pi times a over 2 squared, which would be pi a squared over 4. So those are the areas of the shapes in terms of their in terms of A, right? Now using our formula up here, we need the mass. So we really just multiply that by sigma. So the mass of the square is 4a squared sigma, and the mass of the circle is pi a squared over 4 sigma. Right? Now we also need to find the center of mass along the x for these objects. Okay, so if we're going to look at the square sheet of metal, we're going to call this our origin. Okay, we need to figure out where we're going to call our origin, because this all needs to be relative to a point. Okay. So the x center of mass for the square, we're just going to look at this as 2a, and then we're just going to divide it by 2 to give us A, right? Then the X center of mass for the circle is going to be a bit trickier, right? So the center of the circle should be halfway through the circle, right? So that would be half A right here, right? 1/2 of an A. But then we've got this A over here also. So we'll call that 3/2 A. Now that we have all that, we can plug it up into this equation up here. I'm going to do it down below so that I've got more room. But we've got the mass of the square times x of the square minus mass of the circle, x of the circle, divided by the difference in masses. Okay? Now this is where this math is going to get kind of hairy. We have the mass of the square, which is 4a squared sigma minus, no, sorry, we need to multiply the x, times a, the x of the square, minus the mass of the circle, pi a squared over 4 sigma, times the x of the circle, which is 3/2 a. Then we'll divide by the difference of mass. So we've got 4a squared sigma minus pi a squared over 4 sigma. Now what we can do first, since this is all uniform density, the density doesn't even matter because the density can factor out. So let's do that. Let's do density times, I'm going to combine these. So that's 4a cubed minus pi a cubed. Whoops, I should pay more attention to that one. That is 3 pi a cubed divided by 8. Yeah, divide by 8. Bingo, done. Now we'll factor out sigma here. Then you just have 4a squared minus pi a squared over 4. Okay, so then you can see sigma is going to cancel out there. Now one more thing you can cancel is the a's. So I'm going to rewrite this down here. We'll factor out a cubed up top and a squared down bottom. So you've got a cubed times 4 minus 3 pi over 8. And then we'll factor out a squared down here to get 4 minus pi over 4. So here, a squared is going to get rid of 2 of those 3 a's, just leaving an a. And then you can put this in your calculator to figure out what all of this equals. Long story short, that's going to equal 0.88 a for the center of mass along the x direction. Now, we can do the exact same thing for the y. However, look at the symmetry. Since this is all symmetrical, we're going to have 1/2 a here from, and then you've got a there, right? So this is all going to be the exact same in the y direction because of where we chose our origin. So that also equals our y center of mass. So our answer will be 0.88 a, 0.88 a. And that is our center of mass, right? Which also makes sense. I'll clean this image up again so I can demonstrate. If you look at where the center of mass should be without the circle, without the bite being taken out of it, right? You would expect the center of mass to be right in the center, okay? However, if you take this part out, now there's going to be more mass in this direction, right? So now that center of mass actually moves ever so slightly, because if this is A and A, then 0.88 A is going to be ever so slightly in this direction, right? So you can see that it actually moved down in that direction where more of the mass now is. So that's how we can find the center of mass of an object if now part of the mass is missing. You can actually subtract all of that information to find your answer. Now, last, what we'll do is we'll find the center of other things, not just the center of mass. We can find, for example, number 1 says the center of velocity of a system of particles. Now, all these are going to be system of particles in general, but for the system of particles for velocity, right? Velocity, center of mass of the particles. You take dr, center of mass, divided by dt. Okay, we're going to say r just describes both x and y, right? Instead of saying dx or dy, we're going to combine them to say dr, right? So this is not an x and y, this is in the xy plane. So we have dr, center of mass, divided by dt. So that center of mass idea, okay, let's take out the mass. We've got the summation of the mass of the particles, okay, times dr over dt. So now that we've got the idea that the mass is going, it's just going to be there, right? You're taking the summation of the mass on top and on bottom, times dr dt. So, like usual, we figure that the bottom is going to be just the summation of mass. So you'll say 1 over m. We actually did this in our other derivation if you look back. Then that will be times the summation of mi times dr over dt, which would be velocity. So this is how you could find the velocity of a system of particles, is find the velocity of each particle and the mass of each particle, multiply those, then divide by the summation of masses. Just like we did with center of mass, right? Find the position of each particle, the mass of each particle, then divide by the summation of masses. So very similar to what we did for center of mass. Now, what would you have to measure to find the momentum of the high jumper shown earlier or the astronaut to the right? Okay, so we've got high jumper, astronaut. We want to measure their momentum, right? So usually when we're measuring momentum, it was always some uniform object, right? But an astronaut is obviously not uniform. Human body, not uniform. So what you need to do is you need to, so let's take, whoops, what's going on? Momentum. Okay, we're going to take the mass of the object, okay, take the summation of all mass times the velocity at the center of mass. Okay? So we've got mass times, okay, what we have over here. We'll take that and we'll just plug it in over here. 1 over m times the summation of mivi, because that is our velocity at the center of mass of a system of particles. And a body can just be a system of particles, right? We are just systems of particles. So that m over m will cancel, and then you just have the summation of all mass, of all the mass of all particles, right, times the velocity of the center of mass, right? So basically it just says that if you take all the mass multiplied together by the velocity of the center mass, you will get the total linear momentum of a complex object. Okay, next it asks, what would the acceleration of the center of mass look like? Well, this is going to look very similar to our first derivation for velocity center of mass. This is basically the derivative of velocity center of mass divided by, the derivative of the center of mass velocity over time. Derivative with respect to time. So to get that cm out of there, right, it's the assumption that you've got this summation of masses. So we have the summation of mass, summation of mass, to show that we are summing the mass of the particles, right, for the top and bottom. Then you have same that we did up top. You've got dv over dt. So this will evaluate the bottom to just say that's 1 divided by the summation of masses, right? And then we're multiplying the top So you'd have the summation of mass times the acceleration of each particle, which is very similar to what we had up top, right? So that just shows that when you have when you want to find the acceleration at the center of mass, you take the mass of each particle, the acceleration of each particle, multiply them, or I guess sum them, right? The mass acceleration sum, divide by all the summation of masses, and you'll get the acceleration of the system. Now, last one asks, write an expression for Newton's second law for a system of particles. So if we have Newton's second law, F equals ma, okay, we're now going to rewrite that as the mass of the system of particles times the acceleration at the center of mass. So you have mass times 1 over m sigma mi ai, right? So we took this right out of here, put it right there, just like we did the same right here. So if those masses are going to cancel, what you're really doing is you're taking the total mass of the system of particles multiplied by the acceleration at the center of mass. And basically that's kind of the foundation of all the kinematics that we do. For example, if you are pushing a car up an incline, right, and we're analyzing the forces on that object, we are assuming that you're pushing on the center of mass. We're not thinking about, are you pushing lower than the center of mass? Are you pushing on the tire? Are you pushing on the hood? Are you pushing on the bumper? We just assume you're pushing, you're exerting this force and it's being applied at the center of mass, right? So we actually assume that all objects in our problem so far have been points. Until this chapter, we never really considered that an object may have a complex shape. So this, however, shows that you can assume that if you take a particle, okay, here, you assume that you take the summation of the mass of all the particles and put it at the center of mass. Then you multiply that by the acceleration applied at the center of mass. I guess the acceleration of the center of mass. Multiply those together, you will get the unbalanced force that causes that acceleration, which is really cool. All right, now that is the end of chapter 9, where we went over linear momentum and the center of mass. Then in chapter 10, we will move on to some rotational kinematics.